Hello everyone and welcome back. Today we're going to continue our exploration of the MATLAB programming language and focus on the linear algebra aspects of MATLAB. So the first thing that you definitely need to know how to do when it comes to linear algebra is to define vectors and matrices. So how are we going to define a matrix? So the easiest way to define a matrix, if you already know the values in your matrix that you want to deal with, is as follows. So usually we define this in a row-wise fashion. So the first row of this matrix, let's assume we want to be 4, 5, and 2. And then we want to go to the next column. So to go to the next column, you're going to do a semicolon. And then you can do, for example, 8, 7, and minus 2. And then the next row is going to be, for example, 0, -1, and 4. Now, me personally, I don't like these rows to be in the same, at least, MATLAB programming row. So what I like to do is I actually like to have them on different rows of the MATLAB programming script, and then I can sort of see what the actual matrix looks like, or what it's going to be looking like inside of MATLAB. So what I can do is I can actually display this MATLAB matrix A and just run that, and actually does give us precisely what we intended it to be. Now there are some calculations on matrices that you definitely should be familiar with. One of the types of calculations on matrices that you probably should know is the norm of a matrix or a vector. And there's several different types of norms. For example, there's the L2 norm, which can be calculated by norm a comma 2. There's the 1 norm, you just replace 2 with 1. You could do the infinity norm, the Frobenius norm. There's several different norms, but norm a2 will give you the L2 norm, which is the most common norm that people do use. Right, so that's how we do the norm of a matrix. Let's assume that we want to do, for example, the determinant and trace of the matrix. So the determinant of a square matrix is going to be equal to DETA, and the trace is going to be TRACEA, and that's going to give us the determinant and the trace of that matrix we have defined in A. Now keep in mind the determinant is only defined, at least intrinsically, if the matrix is square. You could do a pseudo-determinant if you want, but we maybe can get to that in another day. So that's how we do determinants and traces in MATLAB. Another calculation you might be familiar with, for example, would be the dot product between two vectors. So let's do v1, and let's let this be a random vector. So a random 4 by 1 vector. So in terms of it being a vector, it has one particular column in it. So that's what the 1 here is. And the 4 is how many rows I want that vector to have. And RAND will give a random bunch of random numbers for that particular vector. So unless you set a particular seed in this randomness, every time you compile this program, that's actually going to give you a different vector. For example, if you run it now, the first element is 0.81. If we run it again, it's 0.63. And every time we run this, that's actually going to give us a different vector. So let's assume we have a vector v1 and another vector v2. Let's also let that be equal to a random vector, say a 4 by 1 vector. Let's assume we want the dot product between them. So that's going to be done with dot, and then v1, v2. So we have vector v1 given to be this vector and v2 given to be that vector, and the dot product between them to be approximately 1.3. So as we already know, if the dot product is equal to 0, they're orthogonal, so we at least see that we have not chosen two orthogonal vectors by random, right? Because their dot product is not equal to 0. The next thing that you probably are familiar with is, for example, solving linear systems of equations. For example, we may be interested in solving ax is equal to b, where a is a square matrix. So we can actually use our previously defined matrix A. The only thing we need to do is do a vector b. So b is going to be the vector, say, 5, -2, and 1. So that is a 1 column, 3 row matrix in a sense, right? So 5, semicolon, -2, semicolon, and 1. So we've actually already verified the determinant of this matrix A is non-zero, therefore this systems of equations is going to have a unique solution. So what is that solution going to be equal to? So there's actually two ways to do this in MATLAB. The intuitive way is doing, for example, the inverse of that matrix A and multiplying it by that vector B. Notice here we do not need the dot operator for multiplication because that's a matrix times another matrix, and the matrix in terms of dimensions is well defined by design. So if I run that, that's actually going to give me the solution to whatever systems of equations that these matrices correspond to. Now there is a more efficient method, and depending on which version of MATLAB you're in, these methods may produce different solutions. But the more preferred way is going to be a backslash b. That also solves the same exact equation, ax is equal to b, but this second method is the more preferred one in terms of which numerical method it has implemented inside of MATLAB. Another calculation that you definitely should be familiar with is the reduced row echelon form of a particular matrix. So we already know that the determinant of A, our square matrix, is again non-zero, so we know that the reduced row echelon form of that matrix should be the identity matrix. So to do reduced row echelon forms, so reduced row echelon forms of matrices, you can just do REF of A. And that's going to give us a, let's actually semicolon these out so it doesn't produce any outputs. Same thing for these. And let's just do the reduced row echelon form of that. So it does produce us the 3x3 identity matrix. But that's not very exciting. So what I want to actually do is define a non-square matrix B, because we know that a non-square matrix cannot have a reduced row echelon form of an identity matrix. So let's let this be a rectangular of the form -4, -3, 6, 7 on the first row, and on the second row let's do -2, 1, 5, and 4. Now let's do the reduced row echelon form of B. Let's block out this A. And that's going to give us the reduced row echelon form of B, and you should already know how to interpret this. So we see that, for example, columns C and D are both dependent on columns 1 and 2. So at least we have two independent vectors and two dependent vectors, but there's so many more applications to reduce row echelon form aside from independence, but those are some of the basics for matrices. Another basic calculation associated to matrices would be the transposition or the transpose of a particular matrix. So let's go ahead and see how we would do the transposition of a matrix in MATLAB. There's actually two ways to go about this. So transpositions of matrices. So the longer way would be just simply transpose of B. So let's actually display B and its transpose just to make sure that this is actually providing you with the correct result. So there's our original matrix B and its transpose. So row 1 becomes column 1, row 2 becomes column 2. So that is the correct transpose. But a shorter way in terms of typing would be B dot and then apostrophe. So that's also going to produce the transposition of the matrix B in a shorter hand, but if you have a lot of code going on, that might look, of course it's a little bit more shorter, but it might be a little bit more complicated or harder to find a mistake, for example, if you're trying to debug your code. But those are two different ways of doing the transposition of your matrix. Now the next thing, of course, is very, very important, has so many applications, and that would be the eigenvalues and eigenvectors of a square matrix A. So we've already defined our square matrix A above, so we're just going to use that same one. So let's assume we want to calculate our eigenvectors and the diagonal matrix consistent of our eigenvalues, and this can be done via the function eig of A. So if we were to go ahead and run that, that's going to produce two elements, V and D, and I'm storing both of them in a matrix which consists of two vectors V and D. So V is going to consist of our eigenvectors, and D is the corresponding eigenvalues. So 12 is the eigenvalue, and that first column is its eigenvector. -1.13 is corresponding to that eigenvector. And the same thing for 4.4, that's going to be the third eigenvector there, at least scalar multiples of them, right? And actually, if you look at these particular eigenvectors, they're actually very, very special. And why is that? So if we look at, for example, the all rows first column, So that's how you choose a particular column. That's actually the very first column of this matrix. And if we do the norm, or the L2 norm of this particular vector, what will we get? Notice that it gives us 1, right? So this is actually a normalized eigenvector, right? Which is very, very useful in terms of applications, but I just wanted to give it to you there because there's actually infinitely many eigenvectors corresponding to an eigenvalue in terms of scalar multiples, but MATLAB actually produces unit vectors for each of the eigenvectors, which is actually very, very nice in several applications. Now, a couple other side things that you may want to do for a variety of reasons, for example, is calculating a vector of ones or zeros. For example, if you want to calculate a vector of ones, that can be done with the command ones. What's the dimension of that matrix that you want? So let's assume we want 5 rows by 1 column. We could also do, for example, a vector of zeros. For example, v zeros would be a with the command zeros and then a 2 by 3. So that's going to give us our corresponding vectors for which we want to build. So that's our column vector of ones and our matrix of zeros, and we could do whatever we want with them depending on our application. Another thing you may want to do is, for example, combine vectors together or concatenate vectors. So what we can do is the following. So what I want to do is I want to first create a random rectangular matrix. Let's call this rectangular matrix xk. Let's assume it's a 5 by 7 matrix, which is given as so. Now let's assume we want to glue a vector of ones with 5 rows and 1 column to the front of this particular matrix. So we want this to be column 2, this column 3, 4, 5, 6, 7, and 8. Right, with column 1 being the vector of ones we defined above. So how do we actually go about that? So let's call that new matrix X, and what we can do is we can do V1s in the first column and then XK in the second column. So what we're actually doing here is we have a block matrix with one matrix in the first or in the left hand side and the next matrix in the right hand side. So if we display that particular vector, notice that all of my ones are there and the rest of the matrix is to the right of it. As we may already know, only square matrices have eigenvalues and eigenvectors. So a more useful decomposition would be the singular value decomposition of a particular matrix. So how would we do a singular value decomposition, or SVD for short, in MATLAB? So singular value decomposition, and SVDs have so many applications in a variety of fields. So singular value decomposition is going to return 3 different things to you. 2 unitary matrices, U and V, and a potentially non-square matrix S, or sigma, which contains the singular values of some matrix of interest. So let's call these matrices U, S, and V, because the singular value decomposition of some matrix A is going to be U, S, V transpose. So in order to do SVDs in MATLAB, that's just going to be SVD. And let's actually not do the SVD of X. Let's actually do the transpose of X times X, so X transpose X. And if you're familiar with some intermediate statistical methods, you actually understand why we want to do the SVD of X transpose X. So one of the things that we usually like to investigate is the stability of a particular matrix, which is associated to the condition number. So if we look at this singular value matrix S, which is given to be this, if we want to do the condition number of this matrix, in this case it's going to be XTX, we would do the maximum singular value, which is 15.7, divided by the smallest singular value, which is something close to 0. And actually we can do a command in MATLAB, which is going to be COND, that's going to give us the condition number for a particular matrix. So let's assume we want the condition number for X transpose X, which is the same thing as doing that element divided by that element there, which appears to be close to 0. So this is going to produce some number that is arbitrarily large, right? Which, at least in the applied sense, is going to imply very bad things, right? But that's how we do condition numbers in MATLAB. Now, once we have our singular value decomposition of a matrix, we could do a variety of different things. For example, we can define the new matrix B to be equal to, for example, V times the inverse of that square singular value matrix. And the only reason that it's guaranteed to be square here is because we know that XTX is always a square matrix, right? So the singular value is also always going to be a square matrix in this case as well. So we have V times the inverse of our singular values. We could do the transpose of that unitary matrix U. We can multiply that by the transpose of the original little matrix X, and then we can multiply it by some random 5-row by 1-column vector, right? And that's going to give us some, random numbers. If you're familiar with multiple linear regression, this statement should look familiar to you. But generally speaking, you could do so much things with a singular value decomposition. That's just one of them. Another very useful thing that you definitely should be able to do with matrices is selecting subsets of matrices. Selecting subsets of matrices. So if we're able to, define, for example, a matrix C, which is going to be a bunch of random numbers, let's assume 5, 9, and then let's comment the rest of this out. So there's our matrix C, and let's assume that we want to calculate, for example, I don't know, the second row, third row, and fourth row, right? So how do we go about doing that? So if I want to grab the second row, a third row, and fourth row, what I can do is create a new matrix, say C sub. And what I can do is I can look in the matrix C. So I want the second row, third row, and fourth row. So that's C2 through 4. And I want all of the columns. So you can just put colon there. That's actually going to give us all rows of 2, 3, and all columns. Or all columns of rows 2 and 3. So there's our row 1, 2, 3, and 4, and there's a row 2, 3, and 4. But 2, 3, and 4 are now rows 1, 2, and 3 of the matrix C sub. Right, so that's how you can grab subsets, and you can do so many variations of that by changing the interior components of this C open parenthesis close parenthesis. But this first portion, 2:4, that's going to be the row dimensions of focus, and that last one is going to be your column focus there. And the last thing that I want to mention here that you might have applications for would be the Kronecker tensor product of matrices, right? Because you can always only do dot product between vectors, but you can take the Kronecker tensor product between matrices. So let's assume we have the first matrix A1, which is going to be a random 2x2 matrix. And let's assume B1 is, let's say, the identity matrix, a 3x3 identity matrix. So the Kronecker tensor product between A1 and B1, which I'm going to call K1B1, can be found by doing KRON of A1 and B1. So let's actually take a look, just in case you're not familiar with Kronecker tensor products. They're actually very interesting tools which can solve a variety of different things. So what we have here is we have our little 2x2 matrix, 0.53, 0.49, 0.69, and 0.53. We have our little identity matrix there, and notice that we have our matrix sort of multiplied by 1, and we have our matrix multiplied by 1 there, and then we have these other two matrices there, which I'm not going to get into to calculate. But keep in mind that the Kronecker product between A1 and B1 is not the same as the Kronecker B1 with A1. For example, if I do K B1 A1, in particular Kronecker of B1 A1, and then display that, notice that they're actually going to give quite different results. In particular, if we have A1 and B1, notice that we have those 2x2 matrices on each of the identity things, but before we're actually doing the identity matrix times the individual elements over 2x2. But more about Kronecker products later, for example, in a linear algebra scenario. But those are some of the basics that you definitely should be aware of when it comes to doing linear algebra in the MATLAB programming language. So I hope you enjoyed, and I'll see you in the next video. Take care.